Okay, so next up we're going to be looking at the concept of a subgraph, and a subgraph is going to be very useful to you as you progress, because if you have properties of subgraphs, you can explain some of your things of your larger graph. In other words, you can make your problems a bit smaller and so on. But obviously, to understand what a subgraph is, you need to know a little bit more set theory. In other words, you need to know what a subset is. So let's start with that. So we have a subset. Now the first thing we're going to need is a set A. So we say let A be a set. And then we can say that B is a subset of A. B is a subset of A if every element in B is found in A. Okay, so something is a subset if every element of that something is found in the element set of that A. And we write it in mathematical notation as B is a subset of A. And that is kind of like a C, but it's not really a C. You know, it's that sideways U in a way. And that's saying it is a subset of. Okay, my handwriting is coming out a bit bad there, so let's just try that again. Subset, don't know what's happening there, of. So let's do an example. We have A is equal to X, Y, and Z. Now we can have B equal to Y and Z. I'm going to write my Z's like that because my Z's can sometimes look like 2's. B could also be, if you're talking about subsets, it could be X and Y. But B could also be X, Y, and Z. Or it could be X and Z. So those are all your options where B is a subset. So the definition basically says it's a subset if every element in B is found in A. Now, one of the other things just to note is that it's a proper subset, and the term proper subset is basically when every element of B is found in A, but it's not actually repeating A, it's the entire set of A. So by that we mean it contains at least one element, A contains at least one element that is not in B. In other words, these ones here are proper subsets because they each, in each of those, A contains at least one element that is not in them. Whereas, so we could also write these B's as that notation. So there is a slightly different bit of notation happening that can happen there. So the idea is you have a subset, and a subset is basically if every element in B is found in A, and then you have a proper subset, and that's basically when there is at least one element in A that is not found in B. We mainly use the concept of a subset. So every element in B is found in A. Okay, now that we know what a subset is, we can actually use that in our definition of subgraphs. So subgraphs, the very first one, we just do the general, what is a subgraph? So we say the subgraph described by, and we're going to call the subgraph H in this case. Again, H is just an arbitrary placeholder, and it consists of your vertex set VH and your vertex set E, not V again, EH, is a subgraph, and we're just going to describe the main graph, subgraph of G, where G is equal to, and we'll describe by, the vertices set of G and the edge set of G, if, and now we're going to have conditions. And conditions are if the vertices set VH, in other words, the vertices set of the subgraph, is a subset of the vertices set of G. And every edge of H is also an edge of G. Now, we could also have simplified that. We can literally just say it as EH is a subset of EG. In other words, all the edges in your subgraph H have to have featured in your main subgraph. So let's do an example. So let's have a main graph, and let's just do this. V1, V2, V3, V4, and V5. A version of a subgraph, again, it's a case of your vertices set of your subgraph must be contained in your vertices set of your graph. So you could have a subgraph where you have just V2 and V3. And then it's also a case of every edge of H is also an edge in G. So right now, as it stands, this here is technically a subgraph of that green graph because it fits those conditions. If you look at it, V2, V3 is contained in, the green set of V1, V2, V3, V4, V5, and let's actually just write that out. VG is equal to V1, V2, V3, V4, and V5. And if you look at this here, VH is equal to V2, V3. So you can see clearly that V2, V3 feature in your VG. So it is a subset of your VG. And then every edge of H is also an edge of G. So right now, we could label it, we could write it out as your EG is equal to, and then we have V2, V3, comma, V3, V4, comma, V3, V5, comma, V3, V1, comma, V1, V5. And luckily for us, our EH is an empty set. So any of the edges in EH do feature in EG because it doesn't feature any edges. Let's do another example just to go through the process. Okay, so a reminder, your VH must be a subgraph of your VG, and your EH must be a subset of your EG. Okay, so that's what you need for it to be a subgraph. So again, let's go through, and we have V1, V2, V3. This is our main graph now. And we want to find a subgraph. So V3, V2, and V1 is a subgraph. Let's do another example from this one. We can have V1 to V2. That's a subgraph. We could have V1, V2, V3 with this happening. That's a subgraph. And then I'm going to have 1, 2, 3, 4. V2, V3, V4. Is this a subgraph? And hopefully you go, we have a whole extra vertex here. So this purple is not an example of a subgraph. Or another example that will not be a subgraph is if you go V1, V2, V3, you add all of these. This technically, at the moment, it is a subgraph. But if I had to add an extra edge, so now suddenly there is a loop by V2, that is not a subgraph because it features an edge that is not in the original graph. Okay, so next up, we're going to complicate things a bit. So we're now going to have a vertex-induced subgraph. And the idea behind it, it describes on how you create your subgraph. So it is going to be a subgraph that's made in a very specific way. So you have your vertex induced, and that already gives you a hint on how you're going to create your subgraph. Subgraph. We need subgraph there. Okay, so it has some conditions. So you're going to have again your graph H, and it's going to be described by VH and EH, and it is an vertex induced subgraph of your main graph VG and EG, described by your vertex sets VG and EG. If, and now what you're going to do is you're first going to have your VH as a subset of your VG. So you're going to find your vertices, and they are going to obviously be a subset of your VG, and then all your edges, so all your edges in your vertex induced subgraph consists of all the edges from your original graph. So all consists of all the edges of your original graph, that graph G, that have both its end vertices in your new subgraph. Both end vertices in VH. So when you create this graph, you select your vertices, and then the edges that come along and become that subgraph are the ones where all the end vertices are in your new graph, that new subgraph that you created. So let's actually just do an example of that. So we have a main graph, V1, V2, V3, V4. Let's throw some edges in there. Okay, now I'm going to create a vertex-induced subgraph. And my VH is going to be V1, V2, and V3. So I start with that. And I put down V1, V2, and V3. Now, all my edges that are going to be in this red graph are edges from the original graph that have both the end vertices in the new graph. In other words, we're going to go look at between V1 and V2. Are there any edges? There are no edges between V1 and V2. So we don't include any edges between V1 and V2 in our red graph. Then we go ahead and look at, are there any edges between V1 and V3? There happen to be no edges between V1 and V3 in our original graph, so no edges take place there. And I'm just going to clean this up a bit. Then we go ahead and look at the edges for V2. So V2, when you look here, you have V2 and V4, and you have V2 and V3. But V4 is not in the new graph, so that one is not going to be included. But for it to be a vertex-induced subgraph, the edge here between V2 and V3, because both V2 and V3 feature in this new red graph, means we have to have this edge featuring in this vertex-induced subgraph. Okay, so when we look at this, we have the vertex, so the vertexes are giving us what the subgraph we're going to look at, and then any edges from the original graph where the end vertices are in the new graph get dragged along and across. So here is your vertex-induced subgraph where your vertices that you're inducing it from are V1, V2, and V3. So one more time, if I just said this, it is not the vertex-induced subgraph. So if I didn't put the edge in there, it is not the vertex-induced subgraph with that VH, V1, V2, V3. So this one's not it. That one's it because it dragged along the edge that goes with it. Let's do another example though. Okay, so let's draw a main graph that we're going to use for our vertex-induced subgraphs. And we have V1, V2, V3, V4, V5, and V6. I'm going to be super lazy here and make it a nice figure 8 style graph. And let's add. Okay, so there's our main graph G, where VG is equal to V1, V2, V3, V4, V5, and V6. And I'm just going to name all these edges. For simplicity, we have E1, E2, E3, E4, E5, E6, E7, E8, and E9. Okay, so we can describe our edge set by just listing them. E5, E6, E7. And remember, when you label this, you didn't have to label your edges. You could have just written V1, V2, V2, V3, and so on. I'm doing this because it's a lot quicker to write. So let's do our first vertex induced. So we're going to create a vertex induced subgraph. And we're going to have our vertex set of our subgraph being V1, V3, V4. So we're going to create a subgraph with the vertices V1, V3, and V4. So let's first actually put those down. Well, let's do it on this graph actually to make our lives easier. So we're going to use this one here, and this one here. Okay. Now, I'm just going to put them over there. So that's what our graph's currently looking like. But now we have to bring in every edge which has both its end vertices in this new graph. In other words, every edge where both the end vertices are those green ones. So in this case, at the moment, if we go look at our graph, it's only that edge there, it's only E8 that actually has both its end vertices in the new graph. So E8. So that there is our vertex induced subgraph with V1, V3, and V4. We have EH equal just to E8. And you can go test to make sure it fits your definition. Okay, let's do another example. Let's just see if I can clean up. Oh, that did not work out very well. Okay, let me just redraw some of this graph. Okay, so we're back to our normal graph there, and we're going to create another vertex induced subgraph. But now we're going to use the vertices V6, V2, V3, and V4. Okay, so we're going to use V6, V2, V3, and V4. So now our edge set for our vertex induced subgraph, where we use V6, V2, V3, and V4, are all the edges where both the end vertices are in the new graph. So if we go ahead and just look at our main graph, it's going to be that vertice there, it's going to be that vertice there, it's going to be that one over there, and that one over there. So we'll have EH equal to E2, E4, E5, and E8. Now, if we had described it without one of those edges, it is not a vertex-induced subgraph. So it has to have all the edges coming through where it has both its end vertices in this new subgraph. Okay, next up we are going to look at something called an edge-induced subgraph. And just one thing to note, if you go look at other notes, a vertex-induced subgraph is sometimes just called an induced subgraph because the edge-induced subgraph is not actually utilized very often. But now we are going to actually introduce your edge-induced subgraph. So edge-induced subgraph. So now that you know what a vertex-induced subgraph is, what do you think would you be using to describe your edge-induced subgraph? Yeah, you will be using your edges. So you'll start off with your edge set, and then you'll look at your vertex set, vertices set. Okay, so you'll have the graph H, which is described by your vertices set VH, and your edge set VH is an edge-induced subgraph of G, where G is described by your vertices set G, VG, and your edge set EG. If, and then you first describe your edges, so you'll have your edges, or your EH, your edge set of H, is going to be a subset of your edge set of G. And then all your vertices for VH consists of all the vertices that create those edges. So in other words, you bring through the edges, but obviously to have an edge, you have to have both end vertices. So you bring through those end vertices for your graph. All vertices that are endpoints or end vertices of EG. Okay, so let's draw an example. So we have V1, V2, V3, V4, and we're just going to throw some edges in here. And let's just call them E1, E2, E3, E4, and E5. So when you do an edge-induced subgraph, we start off with the edges. So you're going to say, okay, EH is going to be equal to, and E2 and E5, for example. So we want this edge in our subgraph, and we want this edge in our subgraph. And let me just bring that back so you can see what we're talking about. So for those edges to exist in our subgraph, they need endpoints, which means we need to bring through this one, we need to bring through this one, and we need to bring through this one. So to bring those edges, for an edge to exist, obviously it has to connect vertices, it has to link vertices, so you have to bring those vertices through. So your vertices set is now going to be that V2, that V3, and that V4. So all the endpoints of E2 and E5. Okay, so let's do some more examples. So we're going to just draw an example for a main graph. I'm going to keep it looking similar to things we've already looked at. Very badly drawn, but you get the point. And you have V1, V2, V3, V4, V5, V6, E1, E2, E3, E4, E5, E6, E7, E8, and E9. Now we're going to create an edge-induced subgraph. So H is going to be equal to, and we're going to induce the subgraph with the edges E1, E3, and E9. So we want this one here, we want this one here, and we want this one here. So to bring those edges across, we need those end vertices of E1, E3, and E9, which means we're going to need V1, we're going to need V2, we're going to need V6, we're going to need V5, and we're going to need V4. And that comes straight from, we look at our edges and we pull those end vertices through to our subgraph. So VH is going to equal to V1, V2, V6, V5, and V4. You can write in order, it's not a big deal if you don't. And if we had to just go ahead and draw this subgraph, we'd have V1 to V2, V6, V5, V4, that over there, and that's E1, that's E3, and that's E9. So that would be our subgraph, our edge-induced subgraph. So the last definition of a subgraph that we're going to look at is actually just a subgraph that is referred to as the spanning subgraph. And the spanning subgraph is essentially a case where all the vertices are taken through, but not necessarily all the edges. So it spans all the vertices. So it takes up the same space as the original graph, spans the space. So spanning subgraph, you have your graph H, your subgraph of H. So the graph H, again described by VH and EH, is a spanning subgraph of G, where you have G described by VG and EG. If all your vertices in VH are the same as your vertices in VG. So they're identical, they have all the same vertices. But the edges are just a subset of the edges of your original graph. So let's look at an example of that. So let's create a graph, V1, V2, V3, V4. Okay, so we have a graph like that. A spanning subgraph, it has to have all the vertices. So it has to have all of these. That is a spanning subgraph of that graph. But another example of a spanning subgraph of this graph, V3 and V4, is if we actually go ahead and put one of the edges in there. That's also a spanning subgraph. It fits the definition, has all the same vertices as the original graph, and the edges are a subset of the original graph. Okay, you can also have a case of, so let's just go on the original graph and say it always has to have V1, V2, V3, and V4. If it doesn't have one of them, it is not spanning. But the edges, it can be a situation. It just has to be a subset.